Welcome back, everybody. I'm really excited to start this chapter 6, which is dealing with all about symmetries, the operators, the symmetry operators, their ramifications, and what it means to be conservative and have conservation laws. Of course, we saw in classical mechanics conservation laws of energy, momentum, all the same things we know and love. And within this chapter, we get to see how things like momentum is the generator of translation. And just on a physical prowess, we see that if I impart momentum to something, it starts to move. Okay, so that kind of makes sense intuitively. Now, I just released a video about how the standard model Lagrangian was made, and in that video, we saw generators. We saw a lot of the group theory aspects of things, and we get to cover a lot of that in this chapter. So if you're interested, definitely stay tuned to this chapter because, as clear evidence, this stuff is used at the highest levels of physics. So it is very important to us to get a good head start on everything. That being said, let's dive into our first question of this chapter. In problem 6.1, he asks us to consider the parity operator in 3 dimensions. Okay, now remember, parity dealt with inversion. So we go from pi of r to psi of negative r. Okay, so we want to show that this is equivalent to a mirror reflection followed by a rotation. And in this particular case, we could see that a reflection and a mirror translation yield the same thing, so the order doesn't matter. And in cases like this, when order doesn't matter, we have in the group theory notation called an abelian group. And we saw that in that last video too. So if you see abelian, that just means it doesn't matter which order you apply them in because they're commutative. Okay? Going into part B then, we want to show that for psi expressed in polar coordinates, the action of the parity operator is pi on psi of x theta, or excuse me, of r theta phi instead of x, y, z, is equal to just a rotation by the angle of pi on the angular terms. And that's pretty darn cool. So you see that parity is intricately linked to rotation. Okay, so some even argue, is parity even necessary when you can obtain the results from rotations and reflections? And, I think it's wise just to have, when we see cases like that, it's wise just to have an operator that deals with it in and of itself. And we see that we have things like parity violation and selection rules that get violated via parity violation or anti-parity, things like that in the standard model. Very important to us. Finally then, in part C, we want to show that for hydronic orbitals, remember how important that Griffiths made this concept of hydronic orbitals back in chapter 4? It's coming back in full force and will forever be a part of what we do within any time we're dealing with atoms. Because hydrogen is the only atom that we have a closed analytic solution for. So if we can model things based on this rendering and apply approximations known as perturbation theories to that model, then we can grasp something and make guesstimates on the higher order terms. And that's why helium turned out to be so hard to deal with, because helium has a mutual repulsion term due to the 2 electrons. And that part of the potential makes it very difficult. But aside from me ranting, we want to show that all that the parity does on hydrogenic-like orbitals is have a -1 constrained with the L variable. And this is very important to us because what we will see later in the chapter is that having this power of L here, whenever we're dealing with operators and how they transform, this leads to selection rules. And selection rules we kind of dealt with the quantum numbers already back in chapter 4. In the brief overview of chapter 5, we saw that selection rules via Hund's rule comes into play too. So be aware, it all ties together. The framework is only getting denser, and trust me, this is only the beginning. Alright then, moving into stop number 1, we have for part A that we were told we want to consider a mirror reflection about the xy plane. Now, I'll have a graphic here in a second, but just understand that when we're reflecting something, the plane itself stays stagnant and the point above the plane gets reflected below. Just like you would see a mirror reflection of yourself, the mirror doesn't move, right? But everything gets projected. Your nose comes in first, and your eyes, things like that. So all we're doing is minusing in the depth perception, okay? So the mirror reflection acting on this state gives us a new wave function, but that just means that we have a negative on the z part, okay? And of course, in computer graphics, we see that this happens in all directions, or we can combine them with rotations to get the inversion that we want. Pretty cool. And by the way, on a segue about rotations, this is where complex numbers and quaternions come in. So if you're interested in quaternions and rotations, group theory is definitely something you want to consider because it is amazing what they can do, especially in computer graphics, which will lead to Clifford algebras and things like that. But now, this isn't just enough to get the parity. We have to now consider what a 180-degree rotation in the xy plane will do. Okay? So if we apply this rotation operator to psi of r, we get the new psi, of course, but this tells us that if I have a point on the z-axis and I simply use that as a pivot, think about like a pencil on the desk and a piece of paper, I can rotate that 180 degrees, and all that does is send my x to a negative value and my y to a negative value, or the opposite value. Okay, so hence we see the results there. Pretty easy to conceptualize here in a basic example. Gets a little more cloudy in some other functions though. So composing these, we see that we have m acting on r, or m or r acting on m, and you get the same result. Because here what we have is, once we see that this is the rotation, you apply the rotation to the psi, you get a new function here, and then you apply the m operator, and you see that you have a negative on the x, negative on the y, m adds a negative on the z, and so we can see clearly that we get the inversion that we're looking for. Now let's see what this looks like though. So here we have the gray, which is the xy plane, okay? Not too big of a deal there. We see here we have kind of a projection, this red line to that red line, this green line to this green line, pretty easy. But note that this green line gets mirror inverted to this green line, and the red line stays intact and everything like that. So this highlights that this is just the negative z that we obtain with the mirror. This is positive z, okay? And now what we have to realize that if we now switch this thing or rotate it by 180 degrees, this comes over here. This is the new line of action. So this is the negative y now, right? Or negative x, doesn't really matter. This comes 180 degrees as well, and this turns into another line, that's negative x. Okay, so all in all, if we apply these two things, we get a negative x, negative y, negative z, and we get exactly what we're looking for. So let's summarize this part A and move on to part B. All right, cool. So clearly that inversion that we saw with the mirror reflection and the rotation leads us to exactly what the parity operator would have led us to. The parity operator, again, is the inversion operator. And we see here that this is exactly what we're looking for. So in conclusion, we know that the parity acting on some wave function or some function at all leads to a mirror and a reflection. Cool, we like that. Again, this is a special kind of reflection. It is a reflection of about 180 degrees, not just some uh, uh, 90-degree rotations or something like that. Has to be 180 degrees. Okay, cool. So we got our first problem checkpoint, and now we can move on to stop number 2, or part B. In part B, we're tasked with, okay, well, let's consider this now in terms of just angular. And what we mean by that is we know that applying the parity operator leads us to inversion of all coordinates. But this is assuming Cartesian coordinates. What if we write these in polar coordinates? Okay, and really this should be spherical coordinates, not polar, but the book doesn't really distinguish. That being said, we see that x, y, and z have this representation. Again, we have to be careful because, theta and phi get mixed up from book to book in notation. Theta is measured from the z-axis from 0 to pi. Phi is measured on the xy plane from 0 to 2 pi. So just be aware, slightly different notation with every book. That being said, we kind of working from a place of hindsight and proving it forward, okay? And the author tells us to go ahead and replace theta with pi minus theta and phi with phi plus theta, or phi plus phi, or pi. I don't know what I'm saying. Pi minus theta. That's why I wrote it down, because clearly I can't speak well today. So let's go ahead and replace these in the coordinates and see what happens. All right. So if we go ahead and follow what the author is telling us to do and put instead of theta pi minus theta, instead of phi pi plus instead of phi we get phi plus pi, easy enough. What we see here is that we get what we need to do is use these sum difference identities, which I have in the PDF. Sum difference identities. Um, Using those, we can clearly see that applying them, we get a something with sine and cosine, something with sine and cosine, both of them. But because it has pi in it, the sines will go to 0 and the cosines will go to -1. And that's what we see in the likes here. Sine here, pi and theta, sine multiplied, we're good. And then we end up with a cosine here with the negative due to the negative cosine that's attached in the sum difference identities. Again, it'll work its way out. That being said, what we see explicitly here is that we have all the same attributes as we did before, but the negative sign puts us with the negative x. Similarly here in the y component, we end up with the negative sign from the sum differences, and that gets factored out, and we have a negative y. And then, of course, the z, the easiest one, gets a negative cosine, so we can pass that to the negative z. Okay, so what we successfully showed is that we get the negatives on the x, y, and z by just a rotation with the angular components. And like I said before, when we see this, we have to be aware that parity and rotation are highly linked together because of this fact. And we saw that some even argued that parity is nothing but a rotation in disguise, which it's hard to deny that looking at this result. Um, but again, we see parity and inversion because of the transformations we have to use in gauge fields, things like that. It has to be a thing in and of itself. So even if parity is just a rotation in disguise, it could also be argued the other way. But rotations are easier to see. So in the other higher level field theories, parity violation, things of that nature, need to be the same and consistent. And parity gives us the mirror and the rotation, so whichever way you want to argue, be aware that some people use it interchangeably. Okay? This tells us that we now can conclude that parity acting in spherical space is just a phase rotation by a phase factor of pi. So pretty cool. Finally, then, we get to part C. Now, this is going to be, we're going to have to make this a little chunky, and this will be the rest of the problem, because we know that hydrogenic orbitals, as stated in the problem, may be written as, well, clearly we saw what the wave function was for hydrogen, but we had a radial part and an angular part. As the result in part B suggests, all we need to do is focus on the angular part, and that's what we'll do. So applying the parity operator to psi of NLM gives us a movement of the angular part itself. So pi minus theta and phi plus pi. Now it's our goal and duty to evaluate what this angular part does. So let's dive into this and see how messy it will become. So with all those things being said, we now get to dive into breaking this into parts. Recall that the angular part of the equation, the angular equation, or the spherical harmonics, was presented in equation 4.32. That being said, we had a coefficient here, which I wrote in long form in the PDF. But, you know, we can't, this is just dealing with L and M as we see here. This has nothing to do with the angles. The angles come in with the other arguments, which is the phase factor e to the I phi and the associated Legendre polynomials. which we see was a function of cosine. Okay, so if we just do what is prescribed here with the angular foundation and add pi to phi, take pi and minus that from theta, we can now evaluate this in parts. That being said, the complex exponential is the easiest one to see here. We break that up, we see we get two exponentials, e to the I m phi and e to the I m pi, but using the rules of exponents, we can put the m up here and evaluate e to the I pi. That's easy enough. We just get a -1 to the m power. So we have a factor of -1 that is added to this whole system here. And we just need to be aware that this is with respect to m. Moving forward, if we use the sum difference identity on the cosine term for the argument of the associated Legendre polynomials, we see here very quickly that we get a cosine of pi, cosine theta, plus, due to the opposite sign here, sine pi, sine theta, and we clearly see why we got a negative cosine theta on part B. This is exactly the identity you would use, easy enough to compute, okay? So putting this result all together, we see that we get an angular equation with a new factor of -1 to the m power, and those associated Legendre polynomial is now of a negative argument, okay? So we need to now look at what the associated Legendre polynomial is. That brings us to equation 4.27. Okay, so since we know that we have a negative argument, let's evaluate what the form is for the negative x. Clearly here we see that we have to put a negative, that's the curly brackets, and curly x here, and negative on the Legendre polynomial itself. Okay, so with that, we're cool, but we see here that the square on a negative just undoes the negative. It does not matter, so we get the negative x squared back. Cool there. This negative goes through the derivative, as you would expect. Constant coefficient style there. Cool, move it through. But we still have to evaluate what the Legendre polynomial itself is with the negative argument. This is quite redundant, quite annoying in many respects, but it'll clean up nicely here soon. All right, so now that we tidy this up, we see that we just have a factor of -1 to the m, thanks to our derivative here, and we can clean up what the Legendre polynomial is by using equation 4.28. Okay, so we see the definition here. Go ahead and plug in the negative argument. We get another squiggly bracket with -x, another squiggly bracket with -x squared. Again, the square undoes the negative, easy enough to see. We have a negative sign from the derivative, so plop that out. So we get a -1 to the L power, and so we saw collectively we have this -1 to the M, this -1 to the L. Let's put that all together for the associated and put it back into the angular equation. All right, cool. Tidy this up. We get just a -1 to the L from the Legendre polynomial. Put this back in with the associated form. See, we get the -1 to the M, -1 to the L. Let's clean this up by taking it all outside. And we see the two factors here that we gained from the inversion is sitting there nicely. And we see that everything in here is the P M to the L, which we see here below it. Okay. And all we did was combine the like powers here, so we end up with the total factor of -1 to the m plus L. Cool. We saw how that happened with the algebra. Now we actually have to put this associated polynomial back into the angular equation. Okay. So let's witness here that we got a -1 to the m from the exponential. Check. And we get a -1 to the m plus L from the polynomial. Check. All right, so with this, we just have to tidy this last expression up, put it together with the summary statement, and we're good to go. Now we can quickly see what we actually have to do and just clean up what actual factor of -1 there is. Okay, so clearly here, we get back the normal polynomial for the angular parts that we dealt with before, as seen here. So we'll check that off. Oops. And what we see is that we have a -1 and we have a factor of m here, factor of m there, so we have two m's total, and plus L of course. But we know that we could split this up pretty quickly, and we see that we have a negative 1 to the 2m and a negative 1 to the L. But notice that this is going to be, if we use the rules of exponents again, put the m outside, we see that we get negative 1 squared to the m power. But negative 1 squared is just 1. So we have 1 to the m power. And we know that 1 times itself infinitely many times is still 1. So we're good there. So we have an overall net factor of negative 1 to the L, which is what we see summarized here. So the angular equation in inversion only has negative 1 based on the orbital angular momentum number L. That's pretty cool. From a rotation on the angles to a negative 1 on the orbital angular momentum. And now you could see why Hund's rules, things like that in this, or excuse me, things like that in the selection criteria are so important. So summarizing this then, what we see here is that the parity acting on a wave function with the hydronic orbital is just broken apart into radial, angular, cool, easy enough. Then in the angular sense, we get a factor of negative 1. This cleans up negative 1 to the L, and then this cleans up to just an overall factor of negative 1 to the L acting on the original state itself. So total inversion just gives us another factor of negative 1 to the L power. That's pretty cool to see. And again, this result suggests that parity is an eigenvalue equation with the eigenvalue of negative 1 to the L. So be aware, this concept will come back to us when we look at how operators transforms and they make the selection rules that we will use in order to see when matrix elements, or even more broadly speaking, tensor elements will be 0 or non-zero. So be aware, very important for us to hold true. So, in conclusion, I'd like to give a massive thank you to our patrons for their invaluable support making all of this possible. Please consider subscribing and sharing this to fuel this curiosity, or even becoming a patron yourself. New content is posted weekly to aid you in your curious pursuits. Again, we see how these building blocks are leading to something very, very big, very, very powerful, and very, very beautiful, but it is very tedious, very difficult, and very labor intensive. So you have to love this stuff to make progress. Okay? That being said, books, notes, and other reference materials are found below. If you have any questions, please feel free to reach out. As always, thank you for watching, and until next time, stay curious.